Greetings, CP Physics. This will be the last podcast for this unit before your test on Friday. Yes, I said Friday. That is Friday the 15th, which also happens to be my birthday. So if you bring cupcakes, maybe I'll take it easy on you on your test. So simple harmonic motion. Simple because it's simple. Harmonic because it's in harmony. So what is simple harmonic motion? It's vibration about an equilibrium position in which a restoring force is proportional to the displacement from equilibrium. That's kind of difficult to understand. It just basically means that something goes away from its equilibrium, then it comes back because there's a force pulling it backwards, and that this is directly related to its displacement. I'll try to clear it up later. Also, when we're talking about simple harmonic motion, we're talking about Hooke's law, discovered in 1678 by Robert Hooke. It's the relationship between the force and displacement in a mass spring system. You have a mass, you have a spring. There's a relationship. And this is what that relationship is. The force, the elastic force, is equal to negative kx. We'll talk about what k and x are in a second, after we talk about who Sir Robert Hooke was. Sir Robert Hooke was English. He worked a lot in biology. He coined the word cell. He also worked a lot with evolution before, Darwin's time. In chemistry, he messed around with vacuums and Boyle's law. And in physics, he did a lot of refraction and wave theory, messed with gravity, and did some law of elasticity stuff. I'll go back in case you didn't get all those. You can just pause it. So, law of elasticity, which we call Hooke's law, and as I said before, big F, the force elastic, equals minus kx. So we have a mass on a spring. In the top picture, it's in equilibrium. And in this picture, it's displaced from equilibrium a distance of x naught, x naught, x0, x naught, x initial. So this dotted line will be its equilibrium position. However far away from it, it gets stretched or compressed. It could also be compressed, is its displacement. And in the equation above, F is the restoring force of the spring. X is the distance that the spring has been stretched or compressed from equilibrium. And K is the only one that is kind of new. K is the spring constant. Each spring has its own K. Some Ks are big, some Ks are small, but they're all measured in the System International units of newtons over meters. So whenever you multiply K times X, X is in meters, K is in newtons per meters. You multiply them together, the meters cancel out, and you're left with newtons, which we all know force is measured in. And the negative sign there is because the force acts in opposite direction to the displacement. So if you stretch it out, the minus sign shows that the force brings it back. If you compress it, the minus sign shows that the force pushes it. So we get the maximum restoring force whenever we displace it, the maximum distance. Makes sense? You stretch it out as far as the string can stretch, you're going to get the most force coming back because that X is going to be big. K is a constant. It's a spring constant. So K stays the same. So the bigger X is, the more force you have, and the max X, you get the max force. And obviously, force is zero at equilibrium because X is zero. So K times X, K times zero gives you zero. So here's some problems. These problems are easy. A 76 Newton crate is attached to a spring with a spring constant of 450 newtons per meter. How much displacement is caused by the weight of the crate? So this one, we're kind of just hanging a spring. We're hanging the mass like from a ceiling with the springs attached to the ceiling, mass is hanging down. So we're given that the force equals 76 newtons. We're given that the K is 450 newtons per meter. We use our equation. The elastic force equals negative kx. We plug in our our givens. 76 newtons for the force, 450 newtons per meter for the K. Don't forget your minus sign. We solve for X, and we get negative 0.17 meters. So this means that the spring is compressed 0.17 meters. So when X is negative, it's compressed. When X is positive, the spring is stretched. Another problem, a spring of constant K equals 1,962 newtons per meter loses its elasticity if stretched more than 50 meters. That means that's its maximum. You can't stretch it anymore. The spring is just going to stretch, and it's not going to come back to its original position. So what is the mass of the heaviest object the spring can support without being damaged? So what's the first thing you think we got to do here? If K is in newtons per meter and the X is in centimeters, you have to convert. So we convert the X, 50 centimeters, to meters. There are 100 centimeters in every meter, so we have to divide the centimeters by 100. There's our equation, Hooke's law. Plug in the stuff we know. You get an elastic force of negative 981 newtons. Force equals mass times acceleration. And since it's hanging, that our gravity here is negative. So the minus sign goes away because you really can't have a negative mass because that would just be silly. Now, using Newton's second law and plugging the stuff in that we know, you get a mass of 100 kilograms. It doesn't always have to be a spring for simple harmonic motion. Sometimes it could be a pendulum. Don't worry about all these cosines and sine stuff. We're not going to deal too much with those. So a simple pendulum consists of a mass called a bob. I don't know why they called it a bob, not a Steve, but they called it a bob, which is attached to a fixed string. There's a thing called a Foucault pendulum. If you ever go to the Museum of Science in Boston, they have one of these right by the coat check room. And this type of pendulum was first used by the French physicist Jean Foucault to verify the Earth's rotation experimentally. As the pendulum swings, the vertical plane in which it oscillates appears to rotate as a bob successfully knocks over the indicators arranged in a circle on the floor. So basically what Foucault did with this thing, he proved that the Earth rotates, and a lot of the naysayers saying that, the Earth was the center of the solar system, they finally had some scientific proof that the Earth is rotating and everything else is rotating too. But a lot of them didn't care because, people don't like science. So the amplitude, we already know this. I don't know why it says 12.2 up there. Ignore that. We already know the amplitude is the maximum displacement from equilibrium. We already know what the period is, the time it takes to execute a complete cycle of motion. We already know what the frequency is, the number of cycles or vibrations per unit of time. We already learned that stuff. And we can find the period of a pendulum and spring with a couple of equations. So for a pendulum, this is what the period looks like. T, which we use for period, the big T, equals 2 pi times the square root of L, which is the length of the string of the pendulum, divided by gravity. This is a lot like Newton's version of Kepler's third law. A lot of the same format. If you remember that stuff from orbital dynamics. And for a spring, it's pretty much the same thing. The period equals 2 pi times the square root of the mass divided by the spring constant. So what is the period of a 3.98 meter long pendulum? We are given the L, the big L, equals 3.98 meters. We know that gravity is 9.81. You can use 9.80 if you don't remember to put the 1 on there. You have the equation T equals 2 pi times the square root of big L over G. You plug in what you know, the square root of 3.98 divided by gravity. Put it in your handy dandy calculator and you get 4 seconds. So you raise the bob of the pendulum up to a certain height. You drop it. It takes 2 seconds to go to the same height on the other side, and another 2 seconds to come back, for a total of 4 seconds. That is its period. What is the free fall acceleration at a location where a 6-meter long pendulum swings exactly through 100 cycles in 492 seconds? So we have 100 cycles in 492 seconds. Sounds like some frequency stuff. We can get the period from that. So we're given that L equals 6 meters. We're also given that 100 cycles in 492 seconds. Frequency, 100 cycles, divided by the seconds. You get a frequency of 0.203 hertz. We know you can find the period from the frequency by dividing 1 by the frequency. And you get 4.92 seconds whenever you divide 1 by 0.203 hertz. Now that we have the period, and we have our equation for the period of a pendulum, plug in what you know. This time we're looking for the acceleration due to gravity. You solve for gravity, and it's roughly regular Earth gravity. We're probably someplace like in Colorado or top of Mount Everest, someplace high where we're further away from the center of the Earth, so gravity is a little bit lower. Yeah, you could pause it. And using a spring, a 1 kilogram mass attached to one end of a spring completes 1 oscillation every 2 seconds. Find the spring constant. We're given the mass of 1 kilogram. We are given the period, which is 2 seconds. This time we're trying to find K, so we have to solve our equation now for K. So we plug in our knowns, rearrange it to solve for K, and you get a K of 9.9 newtons per meter. One more problem. I think this is the last one. A man needs to know the height of a tower, but darkness obscures the ceiling. He knows, however, that a long pendulum extends from the ceiling almost to the floor, and that its period is 12 seconds. You can find out how tall the tower is. We're given this stuff. We're using this equation. We're solving for big L, since the length of the pendulum is almost to the floor. You plug in your junk. You solve for the L. You get an L of 35.8 meters, which is a ridiculously tall ceiling. That's like, 100 feet. And that's the end. Hopefully you printed the notes off before you watch this, and have a good day.